Okay, just picture this for a second. The sun, right? It's always there. Then suddenly it starts to fade. Darkness. Middle of the day. It's an eclipse. Pretty powerful feeling, right?
Oh, absolutely. Visceral is the word. It filled people with awe, maybe even, a bit of fear back then.
For sure. But just knowing why it happens. Earth's shadow, moon lining up, it's only part of it for astronomers, isn't it? For those really trying to understand the cosmos.
Right. The real challenge, the practical need, was prediction.
Exactly. When is it going to start? Critically, how long will it last? And how much? How much light are we going to lose?
It's moving beyond the concept to the specifics.
Yeah, it's not just about the mechanics. It's about unlocking the predictability within something that feels so, surprising. Let's dive into decoding that math of cosmic darkness. Welcome to the deep dive. So if you were with us for our last exploration, that was number 30, you'll remember we talked about Aryabhata, how he basically said eclipses aren't angry gods or anything.
Right, a huge conceptual leap.
They're just shadows. Earth's shadow hitting the moon, or the moon's shadow hitting Earth. Really scientific stuff for the time.
Absolutely groundbreaking.
So now, in this deep dive, number 31, we're shifting gears a bit. We're going from the why, the cause, to the how. How did Aryabhata actually calculate these things?
The applied geometry.
Exactly. In the Golapāda section of his work, he lays out these pretty sophisticated methods to figure out precisely when an eclipse would happen, how long it would last, and even the extent how much dimming you'd see.
It's essentially an ancient how-to guide for predicting eclipses.
You can think of it that way, yeah.
Yeah.
Ancient instruction manual based on geometry. So Aryabhata sets this groundwork. Eclipses are shadows.
Yeah.
Okay.
Yeah.
That's huge because it immediately says, hey, this is predictable.
Right. If it's just geometry and orbits, then theoretically you can calculate it.
Yeah, if you know how big the sun, Earth, and moon are, roughly how far apart they are, and you understand their paths, well, you should be able to figure out when those shadows are going to line up.
And the Golapāda is where he really digs into the how. He builds methodically on that foundation.
Okay, so the first thing he tackles, you can't just have an eclipse anytime, right?
Yeah.
Not every new moon or full moon works. Why not?
Good question. Verse 38 gives us the answer. It lays out two key conditions.
Let's hear it. What does verse 38 say, basically?
Okay, paraphrasing a bit for clarity, it essentially says, an eclipse happens when the moon, while near a node, either reaches the sun at the end of the true lunar month, that's the new moon, or when it enters the Earth's shadow at the fortnight's end, that's the full moon. And then it mentions needing adjustments for the exact timing.
All right, let's break that down. First condition, the phase of the moon.
Crucial.
So for a solar eclipse moon blocking the sun, it has to be new moon. That's when the moon is between us and the sun. Aryabhata calls this, let me see, Sphuṭaśaśimāsānta.
End of the true lunar month, yes.
And for a lunar eclipse, Earth's shadow on the moon, it has to be full moon. Earth between sun and moon. That's Pakṣānta, end of the fortnight.
Exactly. So solar needs that Sphuṭaśaśimāsānta alignment. Lunar needs Pakṣānta. It anchors these dramatic events into the regular, predictable cycle of the moon's phases.
Which is smart, right? It makes them seem less random, more part of the natural order.
Absolutely. It demystifies them to a degree, framing them as consequences of the familiar Earth-Sun-Moon dance.
But like we said, we don't get eclipses every single new and full moon. Thank goodness, maybe.
Haha, probably. It would be less special.
So that brings us to the second condition in verse 38. The moon has to be near a node. Nodal proximity, or Pātāsanna, I think is the term.
Pātāsanna, yes. Being near a pada, a node. This is absolutely critical.
Okay, refresh us on the nodes, the pada.
Right. So imagine the Earth's path around the sun. That plane is called the ecliptic. The moon orbits the Earth, but its path is slightly tilted relative to the ecliptic.
By about 5 degrees, right?
Roughly, yes. The lunar nodes, the pata, are the 2 points where the moon's tilted path crosses the plane of the ecliptic. One where it goes up through the plane, one where it goes down.
Got it. So most of the time, when it's new or full moon, the moon isn't exactly on the ecliptic plane. It's a bit above or a bit below.
Precisely. It has some celestial latitude, or Viṣkambha, as Aryabhata would term it.
Viṣkambha, latitude.
Okay, and for an eclipse to happen, the moon needs to be at the right phase, new or full, and very close to one of those crossing points, one of the nodes.
Pātāsanna.
Near the node.
Yes. Only then is its latitude at Viṣkambha small enough for it to actually line up directly with the sun for a solar eclipse, or pass right into the Earth's shadow for a lunar eclipse.
So it's a two-factor requirement, right phase and right place in terms of that up-down tilt.
Exactly. Without considering the nodes, you'd predict far, far too many eclipses. It requires thinking in 3 dimensions, understanding those orbital inclinations.
Okay, that makes sense. Now, verse 38 also mentions something else, finding mid-eclipse time, Grahaṇamadhyam, and needing addition or subtraction, adikanoan. All right, adikona, meaning adjustments. So calculating the exact moment of new or full moon, that gives you a starting point for the middle of the eclipse, the Grahaṇamadhyam. But it's not quite the final answer.
Why not? What needs adjusting?
The main reason is parallax, Lambana in Aryabhata's terms, especially parallax and longitude.
We talked about parallax before, didn't we? Episode 29, maybe? That apparent shift in position when you look from different places?
Exactly that. Think about it. Someone on one side of the Earth sees the moon against the background stars slightly differently than someone on the other side.
Okay.
So the precise moment of alignment for a new moon, or the moment the full moon enters the shadow, can appear slightly different depending on where you are on Earth.
Ah, so the timing depends on the observer's location.
Yes. Compared to a purely theoretical calculation for the center of the Earth, an observer on the surface will see things shifted slightly in time due to this parallax effect, this Lambana. Aryabhata knew you had to apply these corrections, adikona, to get the accurate mid-eclipse time for a specific location.
That's pretty sophisticated.
Yeah.
It shows he wasn't just thinking theoretically, but practically for observers on the ground.
Very much so. Making predictions useful for people in different places required accounting for these observational effects. It's about what you'd actually see.
Okay, so condition set, phase and node of proximity. Timing adjusted for parallax. Now, let's focus on predicting lunar eclipses. For that, you need to know about the Earth's shadow, right? The Bhūcchāyādīrghatvam.
Precisely, you need to know its dimensions. The sun is much bigger than Earth, so Earth casts a shadow that tapers to a point like a cone stretching out into space.
A cone of darkness.
Essentially, yes. The umbra, the darkest part, is conical. Aryabhata needed to calculate how long this cone is. Verse 39 gives a method for the length of the Earth's shadow, the Bhūcchāyādīrghatvam.
And how does he calculate that length, the Bhūcchāyādīrghatvam?
Well, the verse itself is quite concise. A common interpretation, based on later commentators explaining the geometry, is you take the Earth's diameter, multiply it by the distance from the Earth to the sun, and then you divide that result by the difference between the sun's diameter and the Earth's diameter.
Huh. Okay, Earth's diameter times sun distance divided by sun diameter minus Earth diameter. What's the logic there?
It comes down to similar triangles. Imagine the setup. Sun, Earth, and the pointy tip of Earth's shadow way out in space.
Right.
You can draw 2 triangles, a big one with the sun's diameter as its base and the shadow tip as its vertex, and a smaller one nested inside with the Earth's diameter as its base and the same shadow tip as its vertex.
Ah, okay, I see it. 2 triangles sharing a common point, one inside the other.
And because the light rays from the edges of the sun graze the edges of the Earth to form the shadow tip, these triangles are geometrically similar. Their angles are the same, so their corresponding sides are proportional.
So the formula is just expressing that proportion.
Essentially, yes. It's using the known ratio involving the diameters and the sun-Earth distance to calculate the unknown length of the smaller triangle, the shadow length. Aryabhata would plug in his own values for the diameters and distances, which he gives elsewhere, like in Gk 0.7.
So he's using fundamental geometry on a cosmic scale. That's cool.
It really is. Applying basic geometric principles to figure out something you can't directly measure, like how far Earth's shadow stretches.
Okay, so that gives us the total length of the shadow cone. But the moon isn't usually right at the tip, is it? It passes through the shadow much closer to Earth.
Exactly. The moon orbits at a certain distance. So knowing the total shadow length isn't enough. You need to know how wide the shadow is at the distance where the moon actually passes through it.
Right. What's the diameter of that shadow cone at the moon's orbital distance?
Aryabhata tackles this in verse 40. He calls this width the diameter of the darkness, Tamaso Viṣkambha, specifically where the moon Indu is located.
Tamaso Viṣkambha, diameter of darkness.
Nice.
And the calculation.
Again, it relies on similar triangles, just viewed slightly differently. You know the total shadow length now from verse 39. You know the Earth's diameter, the base of the shadow cone, and you know the distance to the moon.
Okay.
Imagine slicing that shadow cone perpendicular to its axis, right at the moon's distance. Verse 40 provides the formula to find the diameter of that slice. It involves multiplying the Earth's diameter by the remaining length of the shadow beyond the moon.
So Total shadow length, Earth-Moon distance.
Exactly that difference. Multiply that by Earth's diameter and then divide the whole thing by the total shadow length.
Okay, let me trace that. Earth diameter times shadow length minus moon distance, all divided by shadow lengths. It sounds like another proportion calculation.
It is. You're using similar triangles again, comparing the big triangle, Earth's diameter and total shadow length, to the smaller triangle formed by the shadow's width at the moon's distance and the remaining shadow length beyond the moon. It calculates how wide that dark circle, the Tamaso Viṣkambha, is right where the moon indute will encounter it.
And knowing that width, that diameter of the shadow at the moon's distance, that must be super important.
Absolutely critical, because now you can compare that shadow diameter to the moon's own diameter.
If the shadow width is much bigger than the moon gets completely swallowed. Total eclipse.
Precisely. If the shadow width is only slightly larger or even smaller than the moon's diameter but still overlapping, you get a partial eclipse.
And the difference in size would tell you something about how long the eclipse might last too, wouldn't it? Like how long the moon takes to cross that shadow.
Exactly. It gives you the fundamental parameters. Knowing the size of the stage, the shadow diameter, and the size of the actor, the moon, allows you to start predicting the nature and duration of the performance, so to speak.
Wow. So these calculations, they seem a bit abstract, maybe, but they directly link Aryabhata's measurements of celestial sizes and distances,
which he established elsewhere,
to the actual observable features of a lunar eclipse, using geometry as the bridge.
That's the beauty of it. It's applied mathematics, turning theoretical knowledge into predictive power.
And it strikes me, when scientists predict eclipses today, with all our computers and super precise data, they're still fundamentally solving the same problem, aren't they? Figuring out the shadow's dimensions and where the moon will be relative to it.
Absolutely. The core geometric problem hasn't changed. We just have incredibly precise inputs, exact radii, orbital elements determined by gravity models, relativistic effects even.
And massive computing power to crunch the numbers.
Right. But the underlying task, calculating the intersection of the moon's path with the Earth's shadow cone in 3D space, is exactly what Aryabhata was tackling with the tools and data he had. Our methods are refined, but the geometric essence is the same.
It really shows how enduring these basic principles are.
It does. The geometry of light and shadow in space is universal.
It even connects to modern tech.
Yeah.
Thinking about something like the James Webb Space Telescope.
Oh yeah? How so?
Well, it has that enormous sunshield, right? 5 layers, tennis court sized.
Crucial for keeping the instruments cold.
Exactly. And deploying that shield, keeping it perfectly oriented to block light and heat from the sun, earth, and moon. That requires incredibly precise calculations of where those bodies are and where their light and shadows fall in space.
That's a fantastic point. It's a modern high-stakes application of understanding shadow geometry in space, miscalculate, and the telescope overheats.
Right. And looking even further ahead, imagine future missions, maybe studying eclipses on Jupiter's moons, or even exoplanets.
Transits of exoplanets are essentially tiny eclipses.
Yeah. So, understanding how shadows are cast by different sized planets and stars at different distances, that fundamental geometry Aryabhata worked on for our eclipses becomes essential for interpreting what we see light years away.
It really does scale up. These aren't just historical methods, they're foundational principles for astrophysics and space exploration. The geometry is constant.
So looking back at these verses in the Golapāda, it feels like more than just math problems. It's like a philosophical shift is happening too.
What do you mean?
Well, by defining the shadow mathematically, by making it calculable, Aryabhata is taking away the arbitrariness, maybe, the sense that eclipses are just random, scary events.
Ah, I see. Replacing mystery with mathematical law.
Yeah, he's saying, look, this phenomenon, it follows rules. We can understand these rules, we can calculate them. It's a move towards a universe governed by predictable principles.
And notice his approach, it's very systematic, almost like the scientific method we'd recognize today.
How so?
Well, first, define the cause. Eclipses are shadows. Second, characterize the components. Calculate the shadow's dimensions, length, width. Third, model the interaction. Figure out how the moon moves through that defined shadow.
Define, characterize, model. Yeah, that sounds familiar.
It's a problem-solving framework based on observation, measurement, and calculation. It's fundamental to quantitative science.
So these calculations aren't just about predicting the next eclipse. They're about transforming how we see the cosmos itself, from something maybe ominous to something understandable. Clockwork, almost.
Predictable celestial mechanics, yes. a major step towards a rational understanding of the universe.
All right, so in this deep dive, episode 31, we've really gotten into the weeds of Aryabhata's initial eclipse calculations in the Golapāda. We covered the essential conditions.
Phase and needing to be near a node, Pātāsanna.
Right. And then we unpacked how he figured out the basic geometry of the Earth's shadow, the Bhūcchāya, calculating its length, the Bhūcchāyādīrghatvam.
And crucially, its width where the moon passes through, the Tamaso Viṣkambha.
Which basically sets the stage for the lunar eclipse. We know the size of the shadow zone the moon might enter. So where do we go next?
Well, we have the stage dimensions. Now we need to predict the action.
Okay.
Next time, in episode 32, we'll continue exploring Aryabhata's methods. We'll look at how he likely used further geometry, maybe even involving principles related to the Pythagorean theorem, and combine that with the relative speeds of the celestial bodies.
Ah, speeds. Because how fast the moon moves through the shadow determines how long things last.
Exactly. We'll see how he aimed to predict the actual duration of the eclipse, both the partial phases and the total phase, if it happens, and also the magnitude, meaning how deep into the shadow the moon goes.
Bringing those ancient predictions into even sharper focus. Sounds good. More applied geometry from Aryabhata.
That's the plan. More ancient wisdom in action.
Okay. So as we wrap up, maybe something to think about.
Yeah.
Just consider how these geometric principles, the ones Aryabhata was wrestling with over 1,500 years ago, to understand shadows and alignments, are the very same fundamental ideas that let us send probes accurately across the solar system, build incredibly sensitive telescopes, and even peer out towards distant stars and galaxies today.
It's a powerful reminder, isn't it? The universe seems to follow consistent mathematical rules.
Yeah. And our ability to figure out and use those rules, that's kind of amazing. It really speaks to the enduring power of just logical thinking, mathematical reasoning, and trying to make sense of it all. Demystifying the cosmos, one calculation at a time.